Good afternoon everyone, welcome to the next lecture in ENGR 49815. We're going to continue with understanding propeller aerodynamics, and we're looking specifically today at how we can determine the induction factors. So we're going to develop the general momentum theory as Glauert did back in, I say 1943, that's when that book was published, but Glauert obviously wrote it a few years earlier than that. So where we got to yesterday, we derived the thrust coefficient gradients, the non-dimensional thrust coefficient gradients, and I said if you go through and derive the same thing for the torque coefficient gradient, you'll end up with this. I made a small mistake here. This should have an additional x in it. When I wrote it down, I was copying from my own undergraduate notes, and they're pretty. My undergrad notes are pretty good. I must have made a mistake when I copied this down originally, because I went through and did the derivation after one of you lot pointed it out to me, and found that actually there is an additional x in here, and it makes sense, because if we think about what the propeller's doing, propeller's spinning round, and if it's producing thrust, it doesn't really matter. The thrust is just the force that is pulling forwards. It doesn't change with radial position. It doesn't produce more thrust just because I'm further outboard. By contrast, the torque is largely due to the drag on the blade, so pushing back this way, and it's experienced at the hub. So there is a moment arm that we care about. So that moment arm gives rise to this x here. So that should have, I did slightly question it when I was writing it down yesterday why there wasn't a function of x, but I didn't say anything. So I've gone back and checked it, and there should be this x in here. And of course you've all done that when you did the derivation yourself. So you all found it and derived it correctly. Maybe just didn't point it out to me. But we've got these two equations here now. This is what we ended up with. These give us the non-dimensional thrust and torque coefficient gradients for our propeller. We don't often use them, or we won't be in this class using them in non-dimensional form. I just wanted to have them highlighted and have them available so we can see the relationships. We'll try and do some manipulation of them so we can use them in this form. But we will be coupling these with a set of momentum equations. So let's have a look at what we've got in here. I'm going to highlight some terms. Let's use blue. So yeah, solidity, advance ratio, the axial induction factor, the lift, again the advance ratio, the drag, and the advance ratio. Yep, sorry, not the advance ratio, the advance angle. So the advance ratio is J, the advance angle is phi. So let me just highlight all these terms, and the reason I'm highlighting them is because these are things that change as a function of x. So remember, x is our non-dimensional span. X is my non-dimensional span. If I've got a propeller blade that has some radius is defined from the center of rotation. So I've got r is my total radius, and then I've got some displacement lowercase r. Then this exists at non-dimensional radius. X is equal to r divided by r. So it goes from some value at the root, which maybe say 0.2, all the way up to x equals 1 at the tip. So that's what our non-dimensional span is on our propeller. Then we've got these other terms, so let's just remember what these are. So we've got the, I think I call this modified solidity. So we remember that regular solidity is sigma is equal to the number of blades multiplied by the chord divided by pi divided by r, where r is that, whatever that local span-wise radial distance is. Sigma r is b c on pi r here on the total radius. So we've got this modified solidity occurring in all of them. We've got phi, which is equal to the arc tangent of Vn divided by Vt. So this is our normal velocity. our tangential velocity. We've then got A. Now I'm being a little bit lazy here. I should be writing A with the subscript A there. That's my axial induction factor. If I write A on its own, it's always going to be the axial induction factor. We remember that so we have got some velocity perturbation, which is the induced velocity. So this is given a symbol lowercase v. Then we say that A is equal to lowercase v divided by my total flight speed. So we've got that A, or we'll say the axial induction factor is equal to that one there. We've then got lift and drag. Those are our two-dimensional lift and drag. We're not going to have to elaborate what those are. Hopefully those should be commonplace. And then there's nothing else new in here. So we could use these equations to determine the thrust and torque gradient. Let's have a look at the things that we know. So solidity we can get because that's just a function of the geometry. So if we have a propeller blade, if we've got a total propeller, we know how many blades there are, so we know what B is. The chord we can measure, or we know. Pi is exactly 3, or it's about 3.14. R is the distance, and then obviously modified solidity, R is just the total radius of our propeller. So we can determine that. What else have we got here? So we've got that pi, again, it's exactly 3. J, we remember J is V on ND, so those are just, that's going to depend how fast we're flying and how quickly the propeller's spinning, but we know it. A, we don't know yet, so we don't know what A is. CL and CD, well, I'm going to put a tick next to them, because if we know what the angle of attack is, so if we know what's into our propeller section, if we know Vn and Vt, we've got Vr, we can determine alpha, because this angle here is the advance angle, this total angle is beta. So we can determine the angle of attack. And if we can determine the angle of attack, we're working under the assumption for the moment that somewhere we've got some sort of lookup table for our propeller. So we've got CL versus alpha. We've got something that maybe looks like that. And we can say, well, for this angle of attack, we've got some value of CL. And probably we've got something that looks like CD versus alpha. So we've probably got some other table. We can say look up for the same value, we can get our CD out. So again, I'm going to put a tick next to those because we know them. The thing that we don't know at the moment is the axial induction factor. So we've got no means of calculating this yet. So we can not at present determine the actual thrust and torque of our propeller. If we could work out what's going on in these equations, we could then take these. So if we integrate these, from 0 to 1 or from 1 to 0, depending how you talk about integrals, then we could determine the thrust and the torque coefficients for our propeller. We need to know our axial induction factor. We also need to know our tangential induction factor. So let's have a look at this one up here. If we remember this velocity diagram over here, then our advance angle is a function of Vn and Vt. So let's just remember what these are. So Vn is actually equal to whatever our incident velocity is, multiplied by 1, plus the axial induction factor. We've then got Vt is equal to omega r, which is the rotational speed, multiplied by 1 minus, and yesterday I think I called it a omega. Let's call it AT, okay, because AT for tangential induction factor. I'm not sure what I called it yesterday, but we'll call it AT now. So it stands that actually our advance angle is a function of both the axial and the tangential induction factors, along with the actual flight speed of the aircraft and the rotational speed. But we therefore need to know these in order to calculate the advance angle and therefore in order to calculate the angle of attack. So we need some other means to determine the axial and the tangential induction factors. So let me just see if I can dig out a diagram as well. I just realised there's a good diagram that will help us understand the importance of these. The axial and tangential induction factors are pretty small. They're decimals, usually well below 1. A 0.1 for the axial induction factor would be very, very high, which would be a very heavily loaded propeller. The tangential induction factor tends to be an order of magnitude lower than the axial one. Let me just see if I can find my one that I'm looking for. Here we go. Let me copy this down. So I've also included in the papers repository, I've included a link to my dissertation where some of these are included. Be mindful that there's parts of my dissertation that we're going to actually go on and say that isn't correct as we do this course. But this particularly here, this is looking at the thrust coefficient versus, I've actually managed to copy to not cut this off the bottom, probably that's the advance ratio there. So remember J is V on ND. What we've got here, importantly, we've got some data points, which are the crosses here, for different blade setting angles. So this is the A0, which is the setting, how these propellers have been twisted, and then we've increased the forward speed, or these two guys, Evans and Liner, did back in 1951. Took data points, then measured the thrust coefficient. So if we don't include A0, sorry, AA and AT, we get these curves. So for these curves, I've just set AA and AT equal to 0. Now what it means is, it means that the angle of attack is too high everywhere all over the disc, because fundamentally the axial induction factor causes the propeller to feel like it's going faster than it actually is flying. And the reason for that is this velocity increment that's added to the free stream velocity. So what it causes is, if we include them correctly, then we get data points that match our experiment much more closely. So this is then including, and here I've just included what's called annular momentum theory, which is an implementation of the theory that we're going to be following today. So we need some means to determine these. Let me just bring my notes where I'm following up. We're going to get the axial and the tangential induction factors from general momentum theory. So general momentum theory was, as we say, the original axial momentum theory was first presented by Froude and Rankine back in 1865. It's been developed, well, theirs was a really simplistic but beautiful model that it assumed a uniform disk and only axial momentum being imparted. It was extended by Glauert in, I think, 1926, so coming up for 100 years ago, to include a swirl velocity component. So including the swirl is what will enable us to determine the tangential induction factor. So we're going to make some assumptions to allow our model work, and we're following the theory of Glauert. The nomenclature is slightly different. Like I say to you guys, I've included my dissertation in the papers repository for this course. The appendix 1 in there is a detailed derivation of a differential form of this model. Now, there's a couple of slight changes to nomenclature that we're using in this course because I've changed the way that I talk about things since then, but we're largely following the theory from there. And there's some really good diagrams that we can copy and we can use from there. So our assumptions. So our assumptions will be, we're going to replace the propeller by an infinitesimally thin circular disc. I think all discs are circular, but anyway. So we assume that it has the same radius as the propeller itself. What this disc is doing is it's providing momentum to the fluid. But what it's not doing, there's no momentum discontinuity. Sorry, there's no velocity discontinuity at all within a stream tube. So if we look at, so this is my disc here. So we're looking at this from the side now. So we've got an actuator disc in the center. We've got our far upstream where the velocity is just at the free stream, we'll call V1. We've got the velocity at the disc, which we'll call V2. And we've got the velocity far downstream, which we'll call V3. I need to get these diagrams up, or I'm unable to copy all of these diagrams perfectly. Here we go. So if we can think about, I've drawn a sort of a crude 2D version of this. We can include a slightly nicer version. This is a diagram that I made, so I feel at liberty to use this for my notes. So we've got this velocity here. This is a nicer 3D version of this diagram. There's one small change here, and again I've changed my nomenclature slightly. These omegas here, let's call these V omega here. Let's just cross them out actually. Now what these are then the tangential, sorry not tangential, these are the rotational velocities at those conditions, at those points. Rotational, or we can call it swirl velocity. These have units of radians per second. So we don't have any velocity jump. So if we were to look, and let's zoom out a little bit, let's have a look at what's going on with velocities here. So if we were to look at our axial velocity, it starts out at the free stream value and it is accelerating until we hit the disk, and we then hit some far value. So it's accelerating before the disk and accelerating after the disk. So we've got V infinity, V3 and V2. This doesn't necessarily need to be a solid line, that's maybe a little bit misleading. So let's turn this into a dashed line. And let's level this off so it finishes at V2. So again, to remember, with the acceleration of the whole stream tube starts upstream and ends far downstream. So the velocity we've got far away from the propeller. If we were to look at the same for the rotational velocity, or this swirl velocity, there isn't any swirl before we hit the propeller. So if we were to draw something similar now, let's draw rotational velocity. Then we'd have 0 all the way until we hit the disk, and when we suddenly have an increment here, and we then see that swirl increase. Let's draw that as a nicer line until we hit our final value here again. So we've got V omega 2, V omega 3. To cause this variation in velocity, we don't have a velocity discontinuity, but we do have a pressure discontinuity. So there's a pressure jump across the disk. And so if we were to look at this now, this is then pressure. Let's also say static pressure. I mean, static pressure is the only form of pressure, really, but let's have a look at what happens there. So then we've got some, let's say this is ambient pressure, P atmospheric. We're then going to have a decrease because the flow is accelerating up to the disk. Let's draw one line over all of these just to show we're looking at the same condition. There you go, so this is my disk line. We would then have an increase. That's the pressure that's been caused by this pressure jump across the disk, and it's going to accelerate again until we hit our same free stream value. Let's draw this as a dashed line, just to show that's quite a nice diagram now. The two values of pressure we've got here, we've got the pressure in the front, which is the suction side of the propeller, and we've got the pressure in the rear, which is the pressure, or the positive side of pressure. So let's say here, pressure at the rear face, pressure at front face. So then this distance here between the two is our pressure increment, delta P. Now that's directly what's causing thrust in our propeller. Let's just have a look at, so we'll write that down as another assumption. So I've written these down as assumptions. Let's just move these a little, no, let's go in here. Okay, so we've written down as assumptions here. Let's just move these down a little bit. And we'll say here we've got a pressure discontinuity. If I can spell continuity correct. There we go, so we've got a pressure discontinuity delta P across the disk. So because we have got, and in fact, and there's another assumption that we're going to make, we've got an inviscid and irrotational stream tube. Now, because of those, we can then apply Bernoulli's equation. Okay, if you want, you can comment on the video, tell me who first wrote down Bernoulli's equation in equation form. Anyone in my 304 class should know that. And those of you who are just nerds and like otherwise useless facts will also know that. But we can apply Bernoulli's equation everywhere in our stream tube except across the disc. So because we've got that pressure discontinuity, we're doing work on the flow there. We can't apply it. Because we're doing work on the float and because we're changing the total pressure, we're changing the total pressure by that velocity increment delta P, so we can't apply it there. But we can apply it separately upstream and downstream. Okay, so we're going to remember how Bernoulli's equation works. We've got PA plus a half rho V squared plus rho GH is constant. Now for our purposes, we're just going to disregard this last term. We're not really disregarding it, but we're just saying that it's always going to be at the same height within a propulsive stream tube. So we're going to say H is equal to a constant. Therefore, we can just disregard these two. So we're just using the first two terms from Bernoulli's equation. So we're going to apply it first upstream. So this is from region 1 to region 2. Let's just copy this diagram again. So I've got not a very good diagram. 1, 2, and 3 here. V1, V2, and V3. And I'm just going to draw a couple of extra things on here. I'm going to draw these velocity increments. V3, which is this lowercase v. So we can say here that V2 is equal to V1 plus lowercase v2, and v3 is equal to v1 plus lowercase v3. So ultimately the velocity that we need, which is for our axial induction factor, is this one here. It's the perturbational velocity that we add. So we'll say what we want. That's what we're going to try and get out of this. So we're going to apply this Bernoulli's equation upstream. So let's have a think. We've got atmospheric pressure here, but let's call it P1, P2, and P3. We will change those back to atmospheric a little bit later. But P1 plus a half rho V1 squared, so that's our upstream version, is equal to our pressure at 2. So remember here we've got the pressure on the front side and the pressure on the rear side. So it's the pressure on the front side that we want now. So it's PF plus a half rho, and the velocity that we need is V2 squared. So this is upstream. In fact, this is both upstream, so this is, yeah. upstream to disk. So this has to hold true for the whole region from 1 to 2, but obviously not really applying at the disk. So we can then rearrange this for PF. PF is equal to, let's just manipulate the right hand side a little bit more first. We'll say PF plus a half rho, and we're going to say in here, in fact, I'm talking nonsense, let's leave this where we are. We're going to rearrange this for PF, sorry about that, guys. We're going to say PF is equal to P1 plus a half rho V1 squared minus V2 squared. And we'll leave that there. We're then going to apply separately from the disk to the far downstream. Just be careful if you're following along in my notes here, if you're following along from the appendix from my dissertation, I include the axial and the radial velocities in here, which is following some researchers called Rosen and Rand, where technically we should be applying the axial and tangential velocities as part of this analysis. We can then show that actually they're so small that we don't care about them. So just if you're following and you see, well, there's a VA, a VR and a VT, that's why. But for our purposes, we're just going to call these our axial velocities. We're then going to apply separately from the disk to downstream. And we're going to say, well, we've got at the disk, we've got the pressure on the rear side plus a half rho V2 squared is equal to the pressure at 3 plus a half rho V3 squared. We're going to do the same thing that we did before. We're going to rearrange for PR. PR is equal to P3 plus a half rho V3 squared minus V2 squared. So now we've got these two, we've got PF and we've got PR. We can use these to express our pressure discontinuity, which is what's causing the thrust. So the pressure discontinuity is equal to the pressure on the rear side, which is the positive part, minus pressure on the front. When you see me looking a little bit confused like that, it's because I'm working in my monitor and I can see emails coming in and I'm just trying to ignore them. But I should have it turned off really. But we can use these equations that we've developed and let's just zoom out a bit so we can write these in. Pressure on the rear side, we've got P3 plus a half rho V3 squared minus V2 squared minus the pressure on the front side, so minus P1 plus a half rho V1 squared minus V2 squared. So let's look at these terms here, P3 and P1. If we look at up here, the assumptions that we've made is that our velocity at P3 and P1 is equal to the total free stream static pressure. So these two are equal, so they just cancel for our purposes, which is really useful. And we can then see that actually those V2s are just going to cancel as well. So this becomes half rho V3 squared minus V1 squared. And this sort of makes sense because what we're saying here is that the pressure discontinuity, the static pressure rise across the disk, has to be equal to the total pressure rise across the whole stream tube. So since the static pressure at V1 and V2 is equal to atmospheric, the total pressure rise has to then be completely contained within the dynamic pressure. Okay, so it's equal to the dynamic pressure rise from 1 to 3. So now we've got this written down, we're going to look at two different means of expressing our total thrust, and this is going to help us develop a relationship for these velocities V1, V2 and V3, how they interrelate, and ultimately an expression for the axial and tangential induction factors. So we can express the thrust in two different formulations. We can say the first one we'll call pressure thrust. I don't always like the way that we separate them into pressure thrust and momentum thrust. They're the same thing and they're equal to each other. They're not two separate parts of thrust. They're just different ways of describing this whole quantity. So just be careful when we're talking about them as pressure thrust and momentum thrust here. So these are the same thing, these are equal and the same thing. These are equivalent, we'll say. These are equivalent and not distinct. So our pressure thrust, this simply comes from a force is equal to a pressure multiplied by an area. Momentum thrust comes from Newton's second law, which is force is equal to the rate of change of momentum. So F is equal to m dot delta V, which we should be happy with if we've gone through fluids courses till now. So we can express these in two different forms. So our pressure thrust for us is going to be F is equal to the pressure rise across the disc multiplied by the disc area. So our disc area is simply equal to pi multiplied by r squared, although we'll just keep it as a for now because ultimately it's going to cancel with another a little bit later. So we've got our expression for delta p. The expression for delta p was a half rho v3 squared minus v1 squared, and then if we multiply that by the area, we're going to get our pressure thrust for our propeller. And we'll get the total thrust, and we've just expressed it from pressure principles. We can also look at this one here. We can say, well, for momentum purposes, our mass flow rate is going to be equal to the velocity passing through the disc. Well, let's just think about this. So if we've got our stream tube here, at positions 1, 2, and 3. M dot's going to be, for our model, M dot is constant. We assume we've got a stream tube that's not entraining fluid. So we are assuming that m dot is constant everywhere. Now, we don't know A1 and we don't know A3, but we do know A2. So this is unknown, but this is known because this is just the disk area. So our m dot for us is simply equal to the disk area multiplied by the volume, multiplied by the velocity, so the velocity at 2. So remember we've got V1, V2 and V3 multiplied by the fluid density, rho AV. Okay, so we've then got this quantity here, which is going to be our mass flow rate. And then our velocity difference is V3 minus V1. So we've got these two things here. We've got F is equal to these two. These have to be equal to each other. So because they're equal to each other, we can make them so, and then we're going to come across quite a useful observation here. So we'll take the left-hand side, a half rho V3 squared minus V1 squared multiplied by A is equal to rho A2. I've called it A on this side, I've just called it A. Okay, I'll just call it A on the right hand side, I've called it A2 here. In both cases, it is just the disk area. So on the right hand side, I've got rho A, V2, V3 minus V1. So this expression on the left hand side, we can simplify, we can expand this bracket into, this is going to be V3 minus V1 multiplied by V3 plus V1. Multiplied by A is equal to rho A, V2, V3 minus V1. Now some things are obviously going to cancel, the rows cancel, the A's cancel, and then this whole bracket cancels here, leaving us with V3 plus V1 on 2 is equal to V2. So this is telling us that the velocity at the disk is equal to the average of the upstream and the downstream quantities. Let's go a little step further. Let's just write this out. V2 is equal to V1 plus V3 on 2. Let's remember that we can express V2 as V1 plus the velocity increment V2 is equal to V1 plus V3. Remember we said that V3 was V3 is equal to V1 plus the increment 3. So this, we can just collect these terms. We've got 2 V1 plus V3 on 2, which is equal to V1 plus V3 on 2. So these also cancel, and we get V2 is equal to V3 on 2. Now this is a very useful observation for us. What is this saying? This is saying that the velocity induced at the disk, i.e. the bit that we care about because it contributes to the advance angle and it's what contributes to the total effective velocity. So the velocity induced at the disk, which is this bad boy here, is equal to structured this pretty awkwardly, so we'll say the velocity induced at the disk is equal to half of the final value. Okay, so the velocity induced at the disk is equal to half the final value. Now, importantly, it's the final value that gives us the amount of thrust produced. Because if we look at our expression for the momentum thrust over here, in our expression for momentum thrust, we've got V3 minus V1. V3 minus V1 is lowercase v3 here. So this is the bit that gives us the thrust, but it doesn't reach that value until it's all the way downstream, until it's reached its final value. So we've got our expression for the axial induction factor. We can now use this and develop an expression to determine what the axial induction factor is. Okay, so our expression was that we've got AA is equal to V2 divided by V infinity. So actually, for our purposes, we can express this as V2 divided by V1. Okay, so lowercase v2 divided by V1 in this case. So we can then use this in our expression for momentum thrust. We may substitute so F is equal to, what was it equal to? Rho A2 V2, V3 minus V1. Rho A V2, V3 minus V1. So let's change some of these values here, okay? So we've got V2 here. V2 is equal to V1 plus V2 here. We can say actually V2 is equal to V1 1 plus AA. We can then say this one here, this is V3, which is equal to 2 multiplied by V2, which is equal to AA multiplied by V1 multiplied by 2. I just had my wife yelp. Let me just check what that was. Love, are you okay? Lorraine? She's okay. Okay, so we've then, she's painting our bathroom, so I presume it was a minor fall. She says she's okay though, so I'm good. So we've now got these, rather than having these full total velocities, we can now express these in terms of the axial induction factor, the total velocity coming in. Remember that V1, for our purposes, let's make that sure that's an uppercase, V1 is simply equal to our total velocity coming in. So that's the free stream velocity. So we can replace all these terms in here. So F is equal to 2 rho A V infinity. So we've got a V infinity. Let's just check this. We've got a V infinity coming in here, and we've got a V infinity here as well. So we have V infinity squared 1 plus our axial induction factor, and then we've got our axial induction factor again here. So think about what we've got here. As soon as we've got our force, Well, this is actually just our thrust. So if we've got our thrust determined, we could then work out what our axial induction factor is. To determine our thrust, we need our axial induction factor. So we're going to look at how we solve that next lecture. Before we get there, we're going to just do the same thing for the torque. So let's just write what we've got here. So it doesn't include any of the sort of propeller blade terms. So it doesn't include solidity, doesn't include the advance angle, doesn't include rotation. So it's got nothing like J. So let's get rid of it. So it doesn't include omega here. This is purely what we call an actuator disc. So this is just this pressure injection that causes this change of momentum within our flow. So we've got an expression for thrust that doesn't include these. Hence, in conjunction with our blade element expressions, we can then determine the axial induction factor, or hence, for a required or known thrust we can determine our axial induction factor. Okay, so we've got that. We want to do the same thing now for the torque. So we'd like to do the same thing for the torque and the tangential induction factor. So we don't use Bernoulli, we can't use that, but we can rely on the constant, which is that the angular momentum can't increase beyond the disc itself. So we've got this injection of angular momentum, but beyond that, momentum has to be constant. So constancy of angular momentum is one of the fundamental properties of our universe. It's obviously utilized by people like ice skaters, pulling their arms in, spinning faster. So we know that our stream tube is contracting, so it must start to speed up more it must start to turn more quickly as it contracts. So we can use our rate of change of angular momentum in the slipstream we can equate the rate of change of total angular momentum added to the torque that's been added to the slipstream, or to the torque that's being required to drive the propeller itself. So the constant angular momentum between 2 and 3, we're going to use V T2 multiplied by R2 is equal to V T3 multiplied by R3. Now I've introduced some new expressions here. So these are lowercase, remember these are perturbational quantities. So these just refer to the velocity that's been added. Now these are the tangential velocity that's been added. We multiply it by the rotational speed. This is going to give us the total angular momentum now. I'm just going to pause here 1 second. Right, I'm back again. So I'm going through a lot of this from memory, so this is why I'm just stopping. I had to stop there just to check I've not made a mistake with this derivation. So in here, there should be another mass term in here, really, on both sides to get the total angular momentum, but we don't need it because this equation holds true within from 2 to 3. So this has to hold true because these are the only parts that can actually change to give us any variation in our angular velocity. So we're going to introduce a new quantity, which is the swirl velocity. These are tangential velocity. This has got units of meters per second. We're going to introduce the swirl velocity, which is the rotational analog of that. So this is then V omega. And V omega is got the units of radians per second. So we can see that Vt is equal to V omega multiplied by whatever our radius is that velocity is occurring at. So we can express the equation above as V omega 2 multiplied by R2 squared is equal to V omega 3 multiplied by R3 squared. So the torque has got to be equal to the rate of change of angular momentum. So since the only one of these that we can know, we can just pop these into our equation for torque now. So Q has got to be equal to V omega 3 R3 squared multiplied by our mass flow rate. Now if we want to just check our units here, we can just check that we've got the correct, this equation is kinematically consistent. So we can see here that torque has units of Newton meters. So then this has got something that's got units of radians per second, which is equivalent to say 1 over seconds really. So let's change that. Actually, let's just change this to 1 over seconds multiplied by meters squared multiplied by kilograms per second. So then this is equal to kilograms meters per second squared multiplied by meters. Yeah. Okay, so this is then Newton. A Newton we know is kilogram meter per second squared. So this is then the same. Okay, so we're happy. And when I went through my check for this lecture later, I just had to do a quick sense check there. So I do that if I'm not certain I've got something derived correctly. I just check my equations, check that they're check that they're consistent in terms of the units that I'm using. So Q is equal to V omega squared R2 squared m dot. So we can then insert our mass flow rate now. So our mass flow rate was rho a V2. Then our swirl velocity was the tangential velocity divided by the radial distance. looking at this, we might have been able to do this without one of those swirl velocities, but we've got to this point now anyway. We're going to reintroduce our tangential induction factor. So a tangential induction factor is, let me get this back. Here we go. AT is going to be equal to our perturbational tangential velocity added divided by the rotational speed at that point. So that's simply equal to the swirl velocity added divided by the rotational speed in radians per second. So we can use this and insert it into our Q equation. Q is equal to AT omega R2 squared rho A VT, sorry, V2. So now we've got this, we can then remember that V2 is equal to V infinity multiplied by 1 plus AA. So we get AT omega R2 squared rho A V1 1 plus AA. Let's just clear this up, make sure that's clear, that's a subscript there. So we've got this now. We've got expression very similarly here. So what we ended up with here is we had an expression for the thrust that was just a function of the fluid properties, not a function of the propeller itself. Now we've got something the same down here. We've got an expression for the torque that's just a function of those fluid properties. So let's bring this one down. Okay, so we've got this one here. We can see this is then, thrust is then quadratic in AA. And we can see that then the torque is a function of both the axial induction factor and also of the tangential induction factor. So if we go back to our equations from yesterday, we don't easily now have expressions that we can insert. I mean, it would be possible potentially to take these equations that we've just developed now, and this is loading awfully slowly. This is now quite a big document, I think. So it would be ideal if we could take these expressions, rearrange for AA and AT, and substitute them into these expressions here, remembering that we're also going to have to use them to determine the advance angle at each point. Now that's just not really feasible. I'm not even certain if it's possible. So what we ultimately will end up doing is setting them equal to 0 at the beginning, and remembering that because the way these are nicely behaved equations, effectively we can then use an iterative solution to find and converge upon the actual value of our axial and tangential induction factors. There are smarter means we can use to solve for them. We can set them up as a system of equations, system of nonlinear equations, and we can then use some better numerical solver to get the final value. But even an iterative scheme is pretty fast for these sorts of propeller calculations. So we've derived and produced what are generally referred to as the coupled blade element momentum theory equations. So we've produced what are called the coupled blade element momentum theory equations. We've developed those to help us determine the performance of axial propellers. So we got those. We're going to look at implementing them over the next couple of lectures. So that will be next week, where we're coding them up and we are using them to predict the performance of given propellers. We're using all of this to just show we've got these models that work pretty well for axial flight, and we're going to end up showing, well, when we've got non-axial flight, when we've got some form of off-design loading to the propeller, things get really complicated, and a lot of these assumptions we've got in here break down, and we'll discover where they come from. And some of the reasons why they break down, we can go and we can see, well, right here, these start to break down because we're multiplying everything by b, which implicitly assumes that each blade has got the same condition occurring everywhere, all over the disk. So we're going to have a look at means of modifying these equations to come up with some performance models for propellers, and then saying, actually, well, their physical basis might not really be valid for this. So we're going to have a look at some higher order modeling techniques. We'll look at vortex models that help us predict really what's going on and how can we determine the induced velocity for propellers. So that's a lot of stuff today, a lot of stuff yesterday. I hope you guys have been following as we've been going through. This is not something that for all people on this course, even as an undergraduate course, I wouldn't necessarily expect you guys to go through all of this and be able to drive it yourself. I'm following what was my undergraduate notes from my undergraduate aeronautical engineering degree. So this was a third year course in the UK, but we are going through it very quickly as the means to an end here. And then we're going to build upon this to develop a different framework to analyse off-design loading for propellers. So I hope it's been informative. I hope you guys have been following. If there are questions, please ask on Slack. And I hope you're enjoying the balmy weather. And I will see you all in office hours on Friday or in a one-to-one meeting if you've arranged it. See you all soon.